Welcome to the next video in A Course in Real Analysis. This is lesson 4 bounds, the solution video to the exercises introduced in the previous video. So let's recall the first exercise is to show that if a set has a minimum, then that minimum is unique. And so, as I described elsewhere, we'll say that we have some poset ordered by preseq. We'll have some subset of X, non-empty, and assume that it has a minimum, which we'll call alpha. We'll assume that there is this other minimum called beta. And what these together mean by definition is that alpha and beta must both be in the set, and they must both be lower bounds of the set. Now, since alpha is a lower bound of y, and since beta is in y, then it follows that alpha preseeks beta. Since beta is a lower bound, right, just basically do it the other way around so that beta preseeks alpha. Then anti-symmetry tells us that alpha is equal to beta, which is exactly what we intended to show. This is the demonstration of uniqueness. Now, I will comment right now that the same basic argument, right, the same argument mutatis mutandis, shows us that the same argument applies to a maximum. So whenever a set has a maximum, then that maximum is always unique. And I gave as a little sort of like last minute realization that I wanted to do the same kind of argument for a supremum, then and an infimum, so I'll do that now. And so let's just go ahead and state the thing that I'd like to prove, which is that whenever a set has, let's say, I guess, an infimum, then the infimum is always unique. And so we'll call that infimum alpha here. And recall what it means to be an infimum. It means that it is the maximum over the set of all lower bounds. Now, if we imagine that there is another infimum, call it beta, so this is an infimum of y, then it follows that by definition of just what that means, beta is the maximum of the set LBY, right? The set of lower bounds again. But we just proved that the maximum is always unique. So this immediately entails that since alpha and beta are the maximum of the same set, then alpha must equal beta. And that is the whole proof. It's a nice, simple proof building off of what we showed for the maximum. And of course, this claim about the infimum is mutatis mutandis the same, right? The statement of the proof the statement of the claim and the proof, just, substituting appropriate things in appropriate places goes the same way. And therefore, I take this to also prove that the supremum of any set is unique, if it exists. And that, by the way, as I think I've emphasized before, is a big if, right? Not every set has a supremum, not every set has an infimum, and so on. But if they exist, then they are unique. But okay, let's return to the rest of the problem, because I believe we have more to show. Right, and what we're showing here and on the next slide is the proof that if anything is a minimum, and of course there will be a dual for a maximum, but here we'll talk about if alpha is a minimum of some set, or the minimum, we can now say, because we now know that they're unique. So if alpha is the minimum of y, then alpha is the infimum of y. So that's what we're proving here. So to prove that alpha is the infimum of y, well, keep in mind, let's write out, alpha equals inf y means, by definition, that it is the maximum over the set LBY. And let's recall that what is the maximum? The maximum, right? So this holds by definition if and only if alpha is both an element of LBY and also is in the set of all upper bounds on LBY. So that might look like funny notation, but and you may not have realized it when we were talking about, you know, sort of applying the maximum to a set that is already a set of bounds. That what it means is we're kind of stacking the sort of like set bound notation on top of each other, right? We are taking the upper bound of, or an upper bound of the set of lower bounds of y. But if you sort of parse through all the definitions, this is what it means. And so this is what we have to show, right? We have to show that alpha is a lower bound of the set y, and we also have to show that that alpha is an upper bound on the set of lower bounds of y. Now, one of these is trivial, right? What have we assumed about alpha? Alpha is the minimum of y, and immediate from definitions from that, we know that alpha is a lower bound of y, right? That's part of just the definition of being a minimum, is to be a lower bound of the set y. So this, right, the fact that alpha is in that part of the intersection here is immediate. The only thing that we still need to show is that alpha is an upper bound on the set of lower bounds of y. And so for this, we are going to take an arbitrary, I'm going to do this on the next slide too, but basically we're going to say let beta be any element of this set. Sorry, it would be LBY. And we will eventually show that alpha is beta precedes alpha. Right, so that's what it is to be an upper bound on the set, is that if you take anything out of the set, then alpha is bigger, so to speak, or that beta precedes alpha. So that's what I've written here. Let beta be an element of the set of lower bounds of y. Again, we're trying to show that beta precedes alpha. This should be precedes, oops. But anyway, we know that alpha is an element of y. How do we know that? Because it's a minimum. Part of what it means to be a minimum is to be an element of the set. So alpha is in y, but beta is a lower bound for the set y, and therefore, immediate from definitions, beta precedes alpha. That is exactly what we needed. And so we have gotten all the components that we need, right? We now know that alpha is the infimum of y. Okay, let's move on to the next exercise. We'll take a singleton set and show that it has both a maximum and a minimum. No surprise, the single element in this set is both the maximum and the minimum, but let's go ahead and rigorously demonstrate that. So let's choose any element from the set y. The goal, of course, is to show that alpha is a minimum on y. So we're going to try to show that, or sorry, not alpha, A is precedes z, right? That is the goal. How do we show it? Well, z being in y means that since y is just the set of A, then there's only one thing it could be. Z must equal A. And by reflexivity, A precedes A, and since Z is equal to A, then we can go ahead and put that Z precedes A, and by the same sort of logic that A precedes Z. So this one shows that A is an upper bound on the set Y. This one shows that A is a lower bound on the set of Y. And A, of course, is also in y. So since A is in the set and an upper bound, it is therefore a max, the max. And since it is in the set and a lower bound of y, it is therefore the min. And proof complete. Okay, next exercise. Consider a totally ordered set, X ordered by preseq, and take a non-empty finite subset Y. We'll show that it has a minimum and a maximum. We will do this by induction on the size of Y. If the size of y is equal to 1, then the previous exercise already covers this exactly, right? That's just the case of a singleton element, and we know that it has a minimum and a maximum now. So in the inductive case, so right, the base case is trivially covered. Suppose, right, for induction, that n is some number such that if it is the size of a subset y, then that subset y has a minimum. Suppose that we now have a set Z, which has size 1 bigger. Okay, because n is at least 1, then the size of Z is at least 2, but importantly, the most important point for what I'm about to do is that it's not 0, it has an element, right? That's what I'm getting at. Z has an element, it is non-empty because its size is at least 2. And so let's take that element, call it A. Now define a new set Z prime, which is Z, but with A having been removed, since it has one fewer element, then its size is n. And of course, we're doing this because this means that the inductive case now applies to Z prime. For now, let's just focus on the minimum. So Z prime has a minimum, and let's call that alpha. And let's consider two cases. Either alpha preseeks A, or A preseeks alpha. This is precisely the point at which we really need that the ordering is a total ordering, because if it were not a total ordering, we wouldn't necessarily know that at least one of these, one of these two cases must hold. That is due to totality. But okay, now since we know that the ordering relation is a total ordering, then we can make this move, right? We can do this proof by cases. And so in the case where alpha preseeks A, then we have that alpha is a lower bound on the set of all Z, because why is that? Well, it's already a lower bound on Z prime, and so alpha preseeks everything in Z prime. Moreover, alpha preseeks A. Well, when you put that all together, that means that alpha preseeks everything in Z, right? Because everything in Z is either in Z prime or it is A, because that was the only thing in Z that's not in Z prime. So when you put all that together, alpha preseeks everything in Z, making it a lower bound of Z. And since alpha was the minimum of Z prime, then that means alpha is one of the elements of Z prime. Well, that means alpha is one of the elements of Z. So when you put all that together, we now know that alpha is in Z. And so since we have that alpha is in Z, we also have that alpha is a lower bound of Z. Therefore, alpha is the minimum of Z. Okay, now let's consider case 2. This is where we assume that A preseeks alpha. Well, in this case, we're going to show that A is the minimum. Not alpha this time, but still the set has some minimum, namely in this case, A. So let's go ahead and say, well, from transitivity, we have that A preseeks everything in Z prime, right? Because alpha preseeks everything in Z prime, right? So if you had, anything, let's say Z like that. So if Z here was any choice of any element out of Z prime, we know because alpha is the minimum of Z prime, then alpha preseeks that Z. Well, in this case, since A preseeks alpha, then by transitivity, A preseeks Z. And so that means that A preseeks everything in Z prime, right? That's effectively what this gets us, is that A preseeks everything in Z prime. And the only thing left for A to preseek in order for it to pre-seek everything in Z is to pre-seek itself, right? Again, A is the only thing not in Z prime that is in Z, but by reflexivity, A pre-seeks A, and so that gets us that A pre-seeks everything in Z. Well, again, since A is an element of Z, that we knew from the beginning, and now we have shown that A is a lower bound on the set Z, therefore, therefore, A is the minimum of Z. But in all cases, Z has some minimum. Again, I'm going to just say that mutatis mutandis, the same argument can be applied to show the result for a maximum, so I won't go through that. Should be fairly clear. So finally, we'll look at this exercise where if we have a poset, a non-empty subset, and we assume that this non-empty subset has some minimum, then let beta be any element of X which precedes, right? Strictly precedes alpha. We will show that beta cannot be an element of Y. The proof will be very short and sweet. Suppose for contradiction that it is in Y. Then because alpha is the minimum of the set, then alpha must be less than or equal to beta. Well, from the assumption that beta strictly preseeks alpha, then we must have that beta, strictly precedes, and therefore it must preseek alpha. So beta preseeks alpha. Well, now we have this pointing in both directions, and antisymmetry tells us that equality follows. But again, from the fact that beta strictly precedes alpha, part of what that means is that alpha cannot equal beta. So we have that. There's a contradiction, and so our proof by contradiction is complete. Finally, I'd like to end on an invitation to ask questions. If you found anything in this video or in related content in the textbook confusing, please leave a question in the comments to this video. If I can answer them in the comments, I will. And if it's a big enough deal, then I will make a whole video and include it in the playlist.